Chapter 4 does the reverse of what we've been doing so far all year. So far, we've been taking the derivative. Now we are going backwards. We are finding the function it was before the derivative was taken. Okay? When we do that, that is called the antiderivative. We took the derivative, now we're going to take the antiderivative to go back to where we started. Okay? And then pretty soon we'll move into other notation like that. So, suppose you're asked to find the original function and we're using capital F of x. If I give you the derivative function, f of x equals 3x squared. So of these three choices, which could be the original function? All three of them, that's right. Because if I take the derivative of x to the third, I get 3x squared. If I take the derivative of x to the third, I still get the 3x squared, but that minus 2 disappears. And the same thing happens with this guy here, that plus 357. Those constants go away. And it's like I have this guy sitting right here the whole time. And I took the derivative and got 3x squared. So the answer is actually all of them. It's because, so that y right there is because of the fact that these constants disappear. There's a reason why this notation right here is just f of x. It's like I'm giving you f of x equals 3x squared. And then I'm telling you that it is the derivative of some original function, capital F of x. Okay? So the notation here would be if I gave you f of x and I said find the derivative, you'd write f prime of x equals, right? But now the notation that I'm giving you here is that I'm giving you the derivative and I'm calling it f of x. It's just a name, okay? If I called you sunshine, I'd still be referring to you. I'm calling this f of x. It's still the derivative of my original function, which I called capital F of x, okay? It's just a shift in the way that we're thinking about what the derivative looks like. Okay, so actually any constant can be in the original function, and you guys already have a good idea of that. To represent that constant, regardless of what it is, when we find the antiderivative, we're going to use this constant, capital C. We call that the constant of integration. And you have to include it when you find antiderivatives. You have to represent that there could have been some constant there. It could be 0, but it could have been any other number. And it's always there. So every time you find an antiderivative, you must include it. So now the actual answer to the problem, what is the original function if its derivative is f of x equals 3x squared, is capital F of x equals, we know that it's x to the third, plus c. And that's the answer. We have to include that. The process of finding the antiderivative is called antidifferentiation. The process of finding the derivative is called differentiation, so the process of finding the antiderivative is called antidifferentiation. This would be a pretty sweet word on Wheel of Fortune. All right, some notation. You got to remember way back to the last section we did, 3.9. When we learned about writing differential equations, I said, would come into play in the future, and here's why. The knowledge here is useful for the notation that we're going to be using for antidifferentiation. Assuming we're given a derivative function, dy over dx equals f of x. Okay? So dy over dx we know is the derivative of some function with respect to x. Okay? And I'm calling it f of x. The differential would be, it's kind of like I took that dy over dx and moved it over there, right? And we talked about that. So the differential then would become dy equals f of x dx. Don't get queasy on me. We did this. Okay. All I'm doing is taking the derivative form and writing it in differential form. So this form allows me to then find the antiderivative using this notation. The notation we use to denote the idea that we're finding the antiderivative is this. You wind up with y equals this symbol right here, which we'll talk about. Looks like a stretched out s. F of x dx. And then that is what's telling you to find the antiderivative of your original function f of x. When you do, you will get capital F of x plus c. That's the formal notation for what we're doing basically from here on out the rest of the year. So at the bottom, what are the integrand, the variable of integration, and the constant of integration here in this problem? Well, the integrand is that symbol right there. The variable of integration is the variable that we would be taking the derivative with respect to. It's the same idea. So the variable of integration is that variable right there, x. And then the constant of integration we just talked about, that's the constant that we have to include, because when we take the derivative of a function, the constant term disappears. So if we go the other way, we have to include some constant to represent that number, whatever it was. Okay, what we just found, the answer in that notation, was called the indefinite integral. We've been calling it the antiderivative. The indefinite integral is a synonym for antiderivative. They are the same thing. So if you see antiderivative, or if you see indefinite integral, we're doing exactly the same thing. So what is a synonym for antidifferentiation then, if indefinite integral is a synonym for antiderivative? Integration, that's right. Antidifferentiation has a synonym of integration. What about antidifferentiate? Very good. Integrate. So the verb antidifferentiate, to antidifferentiate would be to find the antiderivative. Integrate is the verb for what we're going to be doing. It means the same thing as antidifferentiate. To integrate means to find the integral. Okay? The integral right here. To integrate means to find the integral. The process of doing that is called integration. So that's your vocabulary that you're going to be using for pretty much the rest of the year. We have derivative, differentiation, we have integral, and integration. So for example, find the general solution of the differential equation y prime equals 4. Well, the general solution means that we're going to integrate. So y prime can be written as dy over dx equals 4. The vocabulary here says differential equation. This is not written as a differential equation. How can I write this as a differential equation? Move the dx over. So it becomes dy equals 4 dx. Now what I want to do to find the general solution is to integrate. Okay? I'm going to use that integrand symbol, the integral symbol that looks like a stretch S. Okay? So basically what I'm doing is if I do something to one side, I have to do the same thing to the other. If I integrate this side, I'm going to wind up with y equals. If I integrate this side, I'm going to write integral of 4 dx. And now this notation tells me that I can integrate it. I can find the antiderivative. I can find the integral. Okay, those are all the same thing. So I get y equals. Now what, if I have 4, must it have been before I took its derivative? 4x. Now we have to include the plus c because I could have any number hanging off to the side there, and if I take the derivative of this, the c disappears. So when I take the derivative, I get dy equals 4 dx, or dy over dx equals 4, which is what I started off with. Okay? We're doing the exact reverse of what we've been doing all year long. This is the general solution. So that was your first example of integration. We're just going to do some more problems here, and it's kind of going to be a refresher for you guys because you've seen this already. Let's start using integral notation and the word integral rather than antiderivative. Kind of like in the beginning of the year, we started talking about limits, and we used limits to find derivatives, and then we sort of got away from using limits. We start off learning about antidifferentiation, and then we start using the word integral, and before you know it, we stop using the word antiderivative altogether. okay? That's kind of where we're at right now already. So use the word integral rather than antiderivative, and see if we can develop some rules for common integrals that we are going to encounter, and we're going to let k just be some number. It's just a number, okay? It's a constant. So if we integrate 0 dx, what do we get? No. C. If we take the derivative of some constant, it goes away. It turns into 0. So this would become just some constant. Because now think about it. If I take the derivative of c, it turns into 0. So that must be what it is. Okay. Now k is just some number. I don't know what it is. If I integrate k with respect to x, so remember this is the variable that I'm integrating with respect to here. So this variable is going to appear. If it was a z sitting here, then the z would appear. K is a constant. Yeah, it becomes kx. Don't forget the constant of integration plus c. Think about that one. Go the other way. Take the derivative of some number x, like 3x, take the derivative, you get 3, okay? If I have kx, any number, I take the derivative, and I just get k. Next one, integral of x dx. X squared, that's it. To take the derivative of something and get x, it had to be x squared to begin with. But to get just x sitting here, it had to be over 2, that's right. And then the plus c, the constant of integration. Check it to make sure it's right. Take the derivative, the 2 comes down, the 2 divided by 2 becomes 1, and I'm left with x, and the c disappears, which is what I started with, so this must be correct. How about the next one, integral of x squared dx? One-third x to the third, or x to the third over 3? Plus c. Yes, they are the same, so you can write them either way. For now, if you want to write it like that, that's fine. Down the road, I'll probably be writing it more like this one right here, and that's fine too. And the last one, integral of x to the third dx. And as you're reading that, try to read it like I'm saying it. The integral of x to the third dx is okay, plus c. There you go. So looking over these answers, and we've already talked about this, but let's just repeat it here. Is there a rule that we can develop here? Yeah. I've used only powers here. Let's see if we can write it down. The integral of x to the nth power, don't forget your dx, is equal to x to the n plus 1 over n plus 1 plus c. Very good. That is your first rule for integration. That's the power rule. All right, so this top line here is exactly what you just came up with the exception of one thing. We didn't mention that. Why? Then we'd have division by 0. That's right. If you were to integrate this, you'd have -1 plus 1, which would be division by 0, and you can't have that. So that means that when we have the integral of x to the negative first, something happens, and we don't know what that something is. So for now, we can't do that. Eventually, you'll learn how to deal with that, but for now, we're going to not see this, okay? That doesn't mean any negative exponent doesn't work. It just means that particular one doesn't work. A couple more useful ones that you need to know. These two right here, they should kind of be fairly familiar looking. We've been seeing this notation, not the integral notation, we've been seeing these properties over and over and over again. If I have the integral of a constant times some function dx, that constant can be pulled out. And I can leave it out front and then have the integral of my function dx. Also, if I have two functions that are being added or subtracted, and all of them are being integrated, notice the brackets here, big parentheses maybe, or little parentheses, or little brackets, or something. some way to group these two functions together, then I can apply that integral separately. I can integrate this first guy and then plus or minus integrate that second guy, and that's what that's saying right there. Integrate the first piece, integrate the second piece, and put them back together. And we've been seeing that all year. It's kind of like taking the derivative of several terms. You can integrate several terms in the same way. So here's a nice imperative statement for you. Integrate this. The integral of 3x dx. Well, I'm going to use the properties that we know, the one that we developed and the two that I just showed you, to rewrite this. That constant can go out front. When it does, I get 3 integral x dx. And we know what the integral of x dx is. This gives me 3 times x squared over 2 plus c. Right? Okay. That becomes 3x squared over 2 plus c.
So when you take that constant out, you don't apply it to c?
I was hoping a question like that would come up. Technically, what I have here is that, right? That's what you're asking me. Is that what I have? Yes, it is. This is what I have. I integrated this thing, and it became this, and I have that 3 out front. So that means that I had to distribute that 3 in, so don't I have a 3c sitting here? That's what you're asking. C is a constant, right? If I multiply 3 times that constant, don't I still have a constant? Yep, it's still a constant. So it stays c. Technically, you would write 3c, but then realize that 3c is still a constant. Okay? It doesn't matter that I don't know what it is, because I still don't know what it is. All right, some more examples here. We have the integral of 1 over x to the third dx. What should I probably do here? Yeah, rewrite it. Integral of x to the negative third dx. And then apply the power rule that we just learned. We're going to add 1 to the exponent, so it becomes x to the negative 2 divided by the new exponent, which is negative 2 plus c. Then rewrite that. The negative sign out front, the 2 is in the denominator, and the x squared in the denominator as well, so 1 over 2x squared plus c is your answer. Make sense? Okay, tell me what to do on the next one. How do I rewrite it? So integral x to the 1/2 dx. Now what? Okay, so what do I get? X to the 3/2. We've got to add 1 to 1/2 and we get 3/2. So I have x to the 3/2 over 3/2. Don't forget your plus c. So with this composite fraction here, the bottom, the denominator becomes multiplication of 2/3. So we wind up with 2/3 x to the 3/2 plus c. So in other words, and you're going to do a lot of these types of problems, the constant out front, the coefficient on that term, becomes the reciprocal of this guy. So it becomes 2/3 x to the 3/2 plus c. That's going to happen a lot. All right, this last one, what should we do? We're not going to change anything. We can take out the 2. So let's do that. 2 integral sine x dx. Now all I have to do is worry about integrating sine. So what is the integral of sine? Okay, right. Think about this. The derivative of sine is cosine. That doesn't do it for me. The derivative of cosine is negative sine. That almost does it for me. So I need positive sine, not negative sine. So the derivative of negative cosine gives me positive sine, which means that the integral of sine must be negative cosine. So the integral of this thing is negative cosine. So I have negative 2 cosine x plus c. It takes a little bit of thinking, and you really need to understand your derivatives in order to help you get through the integrals. And you need to remember that you're going integration. You're not going differentiation. And that is the trickiest part of what we're doing here. Most people, when they get confused, start going the other way, and you don't want to do that. How about this one? Integral of 1 over x dx. So first rewrite it, right? It becomes the integral of x to the negative first dx. And earlier we said we can't do that. Why can't we do that again? It results in division by 0, which we can't ever do. And we don't know how to handle that just yet, so we'll just leave it like that. We will get there. We're just not ready for it. Okay, what do I do when I have several things to integrate? Okay, this is using that second property that I showed you, not the power rule, not the first one where you pull the constant out, but the second one where you can integrate separate terms. So what I'm going to do is split this up very formally and rewrite this as the integral of x dx plus the integral of 2 dx. Well, the integral of x dx becomes what? X squared over 2 plus c. Then I have the plus. The integral of 2 dx becomes what? 2x plus c. So now I combine like terms. There's no like term here, so I have x squared over 2 plus, there's no like term for this guy, 2x. And now I have c plus c. Well, c plus c is technically 2c. But that's still a constant. I don't have to change letters or anything. It's just plus c. Okay? So let me go ahead and write that down a little bit better. The c plus c equals 2c, which is still a constant. So that's the same as just saying c. It's always c. Okay, how about this one? We ready for something like that? No. Nope. Rewrite it. Then integrate it. Then simplify it. So if I'm going to rewrite this, what am I probably going to do? Looking for a 5-letter S word. At least it started with S. Split it. So this. I know. I don't know why you guys are having such a hard time with splitting, but we want to split this. So I'm going to rewrite this as the integral of x over the square root of x plus the integral, dx, plus 1 over the square root of x dx. So now it's split. Now we can rewrite it. So this becomes the integral of, this is x to the first divided by x to the 1/2, which becomes x to the 1/2. When you're dividing like bases, you subtract the exponents. Dx plus, this one is the integral of x to the negative 1/2 dx. So let's see if we can talk our way through this integral. Integrate x to the 1/2 dx. What do we get? You'll get faster, trust me. Yeah. So we're going to add 1 to the exponent and get 3/2. And then we're going to picture that 3/2 underneath. We're going to have to leave it, change it, flip it, and that's going to give me the 2/3 x to the 3/2 plus c. Right? Over here we have what? We've got to add 1 to the exponent.
So
X to the 1/2 over 1/2, which leave it, change it, flip it, comes up here, and it's a positive 2. So I have 2/3 x to the 3/2 plus 2 x to the 1/2 technically plus c, so plus c. And there's your answer. Down the road, we might try to rewrite this back down to just one term. Might. But I'd leave it like this. Okay, and very important safety tip right here. The integral of a function divided by a function is not the integral of the top function divided by the integral of the bottom function. It is not that. So please don't do that. Please don't try to do a quotient rule on it. You can't. Okay? Try to rewrite it. Usually you'll be able to rewrite it. As usual, we have to also deal with trig problems. So we want to integrate this one, and we're going to do that by rewriting it, of course, recognizing some identities, and then probably looking up the integral. So first of all, to rewrite this, what should I do?
I would do 1 over cosine, which is...
Okay, so let's rewrite it as the integral of 1 over cosine. What happened to the square?
Oh, I was going to split it.
Okay, times sine x over cosine x dx. Does everybody agree that that is okay? That's okay? If I multiply that back out, 1 times sine is sine. Cosine times cosine is cosine squared. Okay, so nothing has changed here. Well, what is 1 over cosine? Secant. What is sine over cosine? Tangent. So we have secant x tangent x dx. What is the integral of secant x tangent x? I don't know either. So what I'm going to do is look in the inside cover of my book and see if I can find it. What number is it? Number 16 on the inside cover is secant u tangent u du equals secant u, but our u here is just x plus c. What is the u? It's a function, yeah. Our function in this case is just x, okay? The u represented the chain rule when we were taking the derivative, and the u is still the chain rule when we are integrating. So we are going to get into undoing the chain rule, and that's what that u is going to represent. So the answer here is actually just going to be secant x plus c. That's our answer.